Okay, so today we are going to start a Riemann integrability. That's a very important topic. So, so first we discuss what is mean by a partition of an interval. So actually, main aim of this section is you got to find the area under this curve. So actually, suppose a function is defined, f is defined on closed interval a comma b to r, be some function. Okay, now we can draw the function like this. So this is our f of x. So we have to find the area under this curve and then x-axis and then x equal to a and then x equal to b. So our aim is to find the area of this one. That is, this area is denoted by integral a to b f of x dx. Okay, so that is the main aim of this session. So first we define what is partition of the closed interval. So in this section we are going to take the interval is closed interval a comma b. So definition for partition. So partition or subdivision. So a partition are sometimes called subdivision. Subdivision we call P of an interval closed interval a comma b, interval closed interval a comma b is a finite set. Maybe we denote that finite set is x0, comma x1, comma x2, and so on, xn. Okay. Now, such that what is the condition? What is the relation between these things? Such that the first point should be a, the last point should be b. Such that is a equal to that x0 and strictly less than x1, strictly less than x2. Everything is strictly less than xn. So the last point is nothing but b. So in this point, the interval closed interval a comma b in the picture. So otherwise I can take this is our a and this b. So if we take finite number of points, so first point I take x0. So if you take some other point, this is x1. Some other point, this is x2. This is x3, and so on. I take the last point is xn. Now the points x0, x1, xn, x2, etc. xn, we call this a partition of this p. This closed interval a comma b. The length of each subinterval need not be same. Maybe the length is here 1, maybe the length of this subinterval is 2, this length is 1, okay, this length is 1 by 2, anything. Okay, so we can take some other partition. If you take y0, so I take some other point, this is y0 and this is y0, y1, y2, etc. yn. So that is also partition. So for given any interval a comma b, we have a infinitely many partition, but every partition is a finite set. The first point is a0, the last point is b. Okay, the first point is a, the last point is b. The middle points are strictly less than other points. Okay, and this point xi's are called nodes of p. The points xi, are called nodes, the nodes of p. Nodes of the partition p. Okay, so for example, there are infinitely many partition for given interval. So we take some specific example of any interval. So example, first one. So we take, so all this we take closed interval a comma b, a and then b. So I take the middle point of these two, that is a plus b by 2. So if I take these 3 points, that is one of the partition. So I take p equal to a, or if you take just only ab. So this is one of the partition. Is called the trivial partition. Is the trivial partition of the closed interval a comma b. Only the endpoints. partition of the closed interval a comma b. And if you take a plus b by 2 and then if you take some other called q, another partition is a plus b by 2 and then b. These 3 points is also a partition. Is a partition. Partition of the same interval, closed interval a comma b. Okay. So another example, suppose if you take any n in n, so I am going to divide this entire interval into n parts. So for given so in this case, first case I am taking n equal to 1. So it's nothing but the interval we get to divide only one part, that is nothing but ab. So here n equal to 2. That is we can divide the entire interval into two parts. That is I take a plus by this is one part and this is one is another part. So in general, for any n in n, so we have to divide the entire interval into n parts. So therefore, I am writing the xi's are, the xi is nothing but a plus I by n into b minus a. If substitute I equal to 1, what you'll get? So sorry, if substitute n equal to 1, so therefore what is the I varies from 0 to n. Okay. So therefore if you take n equal to 1, the I varies from 0 to 1. Therefore what is x naught? If substitute I equal to 0, we get just a. If substitute I equal to 1 and n equal to 1. Okay. Therefore what is x1 is nothing but a plus 1 by 1, that b minus a. So a cancel, we get b. So for n equal to 1, we get the trivial partition ab. Now if substitute n equal to 2, you will get this second partition q. Okay. In general, xi's are a plus I by n, b minus a. Okay. So now if we collect these numbers xi's, then the partition, the finite set x naught, x1 up to xn is a partition. Maybe we can say the partition is, since this partition depends on n, right? We call p suffix n. Okay. Note that this Pn divides the entire interval, closed interval a comma b into subintervals of each interval is length is always same. Okay. The length of each subinterval. So subinterval means what are the subintervals? So if you take this x naught and then x1. So x naught comma x1, this is one subinterval, and the x1 comma x2 is another subinterval, and so on. The last one is xn minus 1 comma xn. So this is another subinterval. So what is the length of this subinterval? x1 minus x naught is the length of this subinterval. What is the length of this one? x2 minus x1. So etc. What is the length of this? The endpoints, subtraction of the endpoint and then the beginning point. So all this length is equal in this partition. But in general, the length of the partition, subinterval partition need not be same. But in that partition, third example, the length of each subinterval is always same. Okay, because we divide the entire interval into n equal parts. Therefore, the length is same. So these are all examples of partition. So partition of the interval is nothing but it is just a finite set of points. So the starting point is a, the end point is b. You can take middle points are always strictly less than other points. Okay. Now another definition, we say there are two partition PQ. When we say one partition is a refinement of another partition, is one is contained in other. Okay. Suppose one partition contains 10 points, some other partition contains 15 points. Then we say suppose Q is a one partition and P is another partition. Suppose Q is bigger than P, then we say that Q is a refinement of P. Q is a refinement of the another partition P. So in the beginning example, look at that. This AB, the trivial partition is always contained in any other partition because all the partition contains AB, right? So the trivial partition contains every partition. Therefore, every partition is a refinement of the trivial partition, because the trivial partition always contained in any other partition. Look at this P, sir, Q. So Q also contains PQ, sorry, PAB. So therefore, Q is contained in P. Therefore, this partition is a refinement of P. Now look at the third one. So the third one is also, maybe if we take some other called P dash, then P dash is contained in Q, because Q contains 3 points, but this P dash here Pn, sorry, this Pn contains more than 3 points, and then all the points of Q is the points of Pn. Okay, so if some partition Q is contained in P, contains P, then Q is the refinement of P. Okay. Now another definition. Suppose we have two partition P1, P2. The union of that partition is called common partition. Okay. So P1 is a one partition, P2 is another partition of the closed interval A comma B. The P1 union P2. P1 union P2 is called common partition. Is called a common partition of P1, P2. P1 and P2. Okay. So given any two partition, we can find a new partition, that is P1 union P2. That is we called common partition. Okay. Now I already said that, but length of each subinterval need not be same. Okay. Now if we take the maximum length of the partition, the subinterval of maximum length, we call is a norm of the partition. Okay. Okay. Otherwise, if you sum all the subinterval length, you will get the entire length. So for example, so this is our, sorry. So this is our closed interval A comma B. So assume that this is an interval A comma B. So this is A and B. So the total length is B minus A. Okay, length of this interval is B minus A. This B minus A split into some part. Suppose I take this is our x naught. Suppose I am taking this x1 and x2, etc. And this is xn minus 1 and this is xn. So this is one partition. Now, what is the length of this subinterval x1 minus x0 plus what is this length x2 minus x1 and so on. If you, what is the length of the last one plus xn minus xn minus 1. So we can cancel this x1 and then this x2, and then the next one is x3 minus x2. Okay, so this x2 minus x2 plus x2 cancel and so on. You can cancel all the things. So finally you'll get xn and then this minus x0. Therefore this is nothing but xn minus x0. So xn minus x0, xn is nothing but b, x0 is nothing but b, a. So the length of the entire interval is nothing but sum of the length of each subinterval. Okay, this is one subinterval, this is another subinterval. So length of each subinterval, you'll get the entire thing. But I already said that length of this subinterval need not be equal to length of this subinterval. So therefore, the subinterval lengths are maybe different. Now we take the maximum length. So we define the notation delta R. So delta R is nothing but length of the rth subinterval. So if you take the rth subinterval is xr minus, so this delta defined to be xr minus xr minus 1. So that is the length of the interval xr minus 1 comma xr. So this is called rth subinterval. The length of the rth subinterval is nothing but subtraction of xr minus 1. We call is delta r. So the summation of delta r is nothing but b minus a. If you sum all the thing, you'll get this one. So here r varies from 1 to n. Okay. Now this is a property, and then if we take the maximum delta r, that is we define it to be norm of the partition. So the next definition is norm of partition. Given any partition P, we can talk about the norm of P. So we define B norm P. where P is a partition like this x0, x1, etc. xn is a given partition. The norm of the partition is defined to be, or sometimes denote the notation mu of P is nothing but the maximum length of the subinterval. That is, maximum of subinterval's length is denoted by delta r, where r varies from 1 to n. The maximum length of the subinterval we define is the norm of the partition. Okay, maximum length. Okay. So, if for example, if we take the interval closed interval 0, 1. So, if we take the partition 0, 1 by 2, 1, right? These are 3 points. So, I split the interval 0 to 1 into 2 parts. So, one part is, one subinterval is 0, 1 by 2 is the one subinterval. Another subinterval is 1 by 2, 1. Now, what is the length of this is 1 by 2. Okay. What is the length of this? Again 1 by 2. What is the maximum is 1 by 2. Therefore, we call P is the partition 0, 1 by 2, 1. Then norm of this partition is the maximum length is 1 by 2. So, in the same interval 0 to 0 to 1, you can take some other points. Suppose you take 0 and 1 by 3, 2 by 3, 3 by 3 is 1. So, therefore, another partition P1 is 0, 1 by 3, 2 by 3, 1. So, this is another partition. Now, what is the norm of this P1? Is the maximum length of this partition. So, length of this 1 by 2, sorry, 1 by 3, this is 1 by 3, this is 1 by 3. Okay, all are 1 by 3. But here all the length are same. Okay, but you can take a different length also. Okay. Now, these partitions are very important to find the area of the curve, area of the bounded function. Okay. Now, we define two sum. One is upper sum, another one is lower sum. That is a very important thing. What do you mean by upper sum, lower sum? Suppose we have a function f. So, f is a function from closed interval a comma b to r. Is a function is given. Now, what is the graph of the function? Is a bounded function. Okay, because the range is so maybe you can say so we define the integrable only for bounded function. Therefore, f is bounded function. Sorry. So, the condition should be f should be bounded function. That is, f of x is always less than or equal to sum f. Now, what is mean by upper sum? Suppose the graph look like the graph of the function. So, for simplicity, I am writing this. So, this is point A and this is B, because the domain is closed interval a comma b. So, for A, it maps somewhere. So, I take this is our f of A, and for B is maps somewhere. This is f of B. Now, this is a function. You can suppose look like the function like this. This is our function. This is our f of x. Now, we have to find the area under the curve f of x, y equal to f of x. Another curve is, if you take this one, x equal to a. This is one curve. X equal to b is nothing but this line. And x equal to, sorry, y equal to 0. So, therefore, we have 4 curve, y equal to 0 is this nothing but x-axis. Y equal to f of x is the given function. And x equal to a is nothing but this line. And x equal to b. Okay. Now, we have to find the area of this region. Okay, so that is our A. But we know that if we suppose our region is either rectangle or square, we know that suppose this is a rectangle of side AB, then the area is nothing but base into it. That is, AB is the area. Suppose we have a squares of side A, then the area is A square. So we are going to use this idea to find the area of this function, this area, this bounded function. Now, first we have to split this interval into small interval. That is, this is x naught, and suppose I take this is x1, and this is x2, and x3, and so on, and this is our xn. So we take the partition. Now we have to split this entire region into small region. So we can take, we can draw the line. Okay, so sorry, this is actually line. Okay, now we will not get any rectangle here. Okay, but we can extend this, and then we can get a two rectangle. One is smaller one, and another is bigger one, right? So if you connect this, you will get a two rectangle. One is smaller rectangle. This inside inside this region. One rectangle is outside region. Okay, so if you join this line, you'll get this one of the partition. Now look at this. So how we define the upper sum and lower sum. So you have to take the minimum value of the, suppose if you take this interval, sub interval x naught comma x1. If you consider this interval, in this interval the function have a both minimum value and then maximum value. Okay, so the minimum value is nothing but in this interval, this is the minimum value, and what is the maximum value? This is the maximum value. Okay, so therefore if you take any sub interval, the sub interval have a the function have a minimum value as well as maximum value. Suppose if you consider this interval x1 x2, so what is the minimum? So this is the minimum value, and what is the maximum? This is the maximum value. Okay, and if you consider this x2 x3 interval, so what is the minimum? Minimum is this one, maximum is this one. Okay, because this is smaller one, this is a bigger one. Therefore any interval, any subinterval, the function have a maximum value as well as minimum value. Now we define what is the upper sum. So upper sum is nothing but you have to take the max. Okay, so now we define for the given partition P equal to x naught, x1, x2, etc., xn, given partition, we define upper sum of the function. So that is u p comma f. That is upper sum of f with respect to this partition. So this is nothing but I take the, okay, before that we define capital Mi. So Mi is nothing but the maximum value of the function in the particular interval xi minus 1 comma xi. So that is nothing but supremum of or maximum or supremum, because it's not a finite set, therefore we can talk. So it's an infinite set. Any interval is an infinite set. If we consider this interval xi minus 1 comma xi, in this interval the function have a maximum value, right? So that is nothing but supremum of all the f of x, where x varies in the interval xi minus 1 comma xi. So in the particular interval, if you take this is xi minus 1 comma xi, so in this interval, what is the maximum value or the supremum of the function? So this is the supreme value in this particular interval. So we call that is Mi. If you take the first interval, that is M1, is the maximum value, this one. So this is M1 and this is M2. Okay, so therefore for each interval, we have a minimum value, maximum value of the function. Minimum value, we define small mi. So therefore similarly, we define small mi is nothing but infimum of the function in the ith interval. That is x varies in the ith interval xi minus 1 comma xi. Okay, if you take any subinterval, the function have a minimum value, we call as mi, small mi. The same subinterval, the function have a maximum value, we call capital Mi. Okay, therefore each subinterval, the function have a minimum and then maximum value. Now we have to sum all these things, but provided you have to take. Now maybe I will explain one more thing. Now here is this. So you consider the upper triangle. this is very crucial part. So how we define this upper sum, lower sum, and then you have to vary all the partition, you will get a exact value. Okay. So this is our okay. Okay, suppose we have a points and then we have function. Suppose we assume that this is our function f of x. Now this is our a. So therefore this is a point a and this is point b. So we take the partition, this is x naught. Suppose I am taking this is our x1. Now I consider only one subinterval now. So I want to find the area of this one. Okay, sorry. Okay, so our game is to find the entire area. So therefore, first I got to split small area and then find the area of the small region, and then I got to sum all the small thing. We will get the entire thing. Now, therefore, in this subinterval, the function have a two value, minimum value, maximum value. So I think this is the minimum of the function in this interval. So this is small m1, and this is the maximum value, capital M1 of this interval x0 comma x1. Now we have a two rectangle. Suppose I am taking this small one, smaller thing. So now I can make a rectangle here. Suppose I draw the straight line here. Now I get a rectangle here. So what is the area of this rectangle? Height into base. So what is the height? So that is the maximum value is this small m, right? So sorry, minimum value. So this is height is m1. What is the length? The base is x1 minus x0. Okay. Now we get m1 into x1 minus x0. You get a small region. We get the area of the small region, this thing. Okay. But this is not a required area because we have to miss something, right? So this area is missing. Anyway, so for this partition, now we have to find what is the area. Now I take the next point x2. Now I have to draw the line. Now I have to make the rectangle. So suppose I think if you draw the line, you'll get this one. We get a rectangle. So this is a small m2 now. And this is capital M2. The maximum point is on the graph is nothing but this is capital M2. Now, anyway, we get a small rectangle like this. So what is the area of this rectangle? Height into base. What is height? Small m2. Base is x2 minus x1. We have to sum it. So plus m2 is the height of the second one into the length is base. That is base length is x2 minus x1. So and so on. If we take the last interval, suppose this is xn and this is xn minus 1 and this is xn. If you take this subinterval and then you can draw the line. Now we form a rectangle like this. If you can draw the straight line here. So this is a minimum value. This is m suffix n. And this is a maximum value, capital M suffix n. Now we get a rectangle here. Now what is the area of this rectangle? Base into height. What is the height? Small m suffix n. What is the base length? Xn minus xn minus 1. So therefore and so on plus mn into xn minus xn minus 1. So now we get some area, but that is not a required area because we miss some portions. Okay, so we miss these portions. So in the last interval, we miss this portion, and here we miss this portion. Again, here we miss this portion, right? But we have to cover the entire thing. Now we can form another rectangle. So I will get another rectangle. Suppose I can look at the first one. I can extend this line into a little bit more, and then I can draw. I can form here rectangle. Now we get a new rectangle, bigger one. In the subinterval x0 to x1, I get a new rectangle. Okay, what is the height? So this is the maximum point. That is capital M1. that is height into base. Okay, so that is capital M1 is the height, base is x1 minus x0. That is the area of the bigger one. Now here we cover the extra portion, right? Because here we cover this portion, extra portion, but we don't want the extra portion. We want to lose our portion. Therefore, we need exact area. So anyway, so now we get some extra portion. Now look at the second rectangle. So second thing. So maybe we can extend this into smaller thing, and then you'll get something rectangle. Now we get this is actually M2 into base. So in general, the final one. So we can extend this line into this, and then we can form the rectangle. And what is the height? Capital Mn. What is the base? Xn minus 1. So similarly, we can extend it. So we get M2 into x2 minus x1 plus etc. plus Mn into xn minus 1. So this is a lower sum, that is LP comma F, that is lower sum of the function with respect to that partition P, and this is upper sum of the partition, upper sum of the function with respect to the given partition P. Okay. Now from this area, the upper sum cover max more area than the smaller region. Therefore, what is the relation between this L of P comma F and then U of comma F? So L of P comma F is always smaller than or equal to U of P comma F. Okay, for any partition. Okay, for any partition P, the lower sum is always less than or equal to upper sum. So this is called the upper sum of upper sum of a function of a particular partition P. So again, this is called the lower sum. Okay, this is called the lower sum of F with respect to P, with respect to the partition P. Now, if you increase the partition points, so the number of points is increasing. So suppose this partition contains n points. Suppose if you split, suppose I take one more point here. Suppose I take some x1 dash or something. Now, if you reduce this, you'll get a, now you'll get here, look at this rectangle. You'll get an exact rectangle. Okay. So therefore, if you increase the number of points in the rectangle, in the partition, the upper sum reduces to the curve, and then the lower sum increases to. So therefore, if you increase the partition, this upper sum reduces to reduces, the lower sum is increases. So therefore, they will meet at some point. So if you increase, you got to vary the partitions. Okay, so I am going to take U of the upper sum of a function. Okay, sorry. I am going to take the infimum of all the upper sum of these, but I am going to vary the partition P. If we increases the partition points, the upper sum reduces. Then you have to take the minimum one or infimum one. So that is, we define it to be upper integral or integral a to b bar f of x dx. Again, for all partition, we can find the lower sum, and then in that you have to take the supremum. So supremum over all the partition L of P comma F, we define it to be lower integral, that is a suffix bar P f of x dx. This is called the upper integral. And this is called the lower integral. So for upper integral, you have to take the infimum over all the partition. Therefore, this upper sum reduces to the exact value. Again, this lower sum, you have to increase run over all the partition is increases. Okay, so that is the main area. So that is, if you look at the first interval, so maybe I erase something here. So there is a main crucial point here. Suppose if you increase the number of points in the sub partition, the upper sum is reduces. the lower sum is increases. Okay, suppose this is a curve, and suppose this our first partition contains x naught and then x1. Suppose if you divide some more points here, you will get some more points in the rectangle, the partition. Now look at here. Maybe here we'll get exact rectangle. So if you split small region, maybe sometimes you'll get a exact rectangle. So now, but in the previous one, you'll get this portion, but here we omit that portion. So if the number of points on the partition is increases, the upper sum is reduces, but the lower sum is increases. So the upper sum and the lower sum meet somewhere. So if they meet, then we say such a function is integrable. So that is, we define the infimum of all the upper sum, where P is the partition over all the partition of closed interval a comma b. We call is a integral a to b bar f of x dx, that is lower integral. For lower sum, you have to take the supremum for all partition. We call it a lower integral. If so, what is the relation between these again? The lower integral is always less than or equal to upper integral. That is integral a bar b f of x dx is less than or equal to integral a b bar. Upper sum, upper integral always bigger. Okay. Suppose both are equal, then we say f is integrable, and then we denote by integral a to b f of x dx. Okay. That is if suppose both are equal, that is lower integral of a function equal to the upper integral of the function, both are equal, then we say f is Riemann integrable. F is Riemann integrable, or simply say integrable. F is Riemann integrable, or simply integrable function. Okay, and the common value is denoted by, and it is denoted by, and is denoted by just integral a to b f of x dx. Okay, and this is actually called area. So this is actually called area of the function, area of the curve under this curve, area of the region under the curve y equal to f of x. Okay. Now we discuss some example. So when we say a function is integrable, if the lower integral and the upper integral is equal, then we say is a integrable function, or sometimes called Riemann integrable. Now we have some theorem. What is the relation between these? Already we mentioned that what is the relation between the upper sum and the lower sum. Okay. One more thing is there. So in the graph, look at the graph. If you take the entire thing, so you can look at this bigger rectangle. If you look at this bigger rectangle, so what is the maximum? We define maximum is capital M. So maximum of entire interval. Small m is the minimum of the entire interval. Okay, but mi is nothing but maximum of the particular interval, ith interval. Small mi is the minimum of the particular ith interval. But capital M is nothing but maximum of the entire interval. So we'll get the entire thing. If you take the minimum rectangle, you'll get a small rectangle, another rectangle. So therefore, the relation between, so maybe I can draw a picture here. Suppose this is our function bounded by this curve. Now we form a new rectangle. So what is another new bigger rectangle is nothing but this. So what is the area of this bigger rectangle? Base into it. What is the base? Actually, this is a point A and this is B. So base is B minus A. What is the maximum value? Is M. So therefore, M into B minus A is the area of this rectangle, the entire thing. But We need only the small thing. Okay. Now we can find a one more subinterval. So this actually m into b minus a is the area of this rectangle. Now if you consider this area, this is smaller one. Now if you find this one, so what is the area of this one? Again, the length is base is b minus a, but what is the height? The small m, minimum. So therefore, what is the relation between these? So we can write here m into b minus a is always less than or equal to the lowest sum of the function for any partition P. The lowest sum is always less than or equal to upper sum of the partition this, and this upper sum is always less than or equal to m into b minus e. Okay, so this is a relation between the upper sum, lower sum, and this thing, where m is nothing but small m is infimum of all the function value, where x varies in the entire interval, and capital M is nothing but supremum of the function or the maximum value of the function for the entire interval. Okay. Now some more theorems are there. Suppose there are some two partition P1, P2, then what is the lower sum, what is the upper sum, what is the relation between these things? So I already said that if the number of points is increases, then the upper sum reduces, the lower sum is increases. Okay, that is the theorem. So the main concept is that's it. If you increase the number of points in the partition, the upper sum reduces, the lower sum is increases. So theorem, suppose we have a two partition and for a function, bounded function. So the Riemann integral will be defined only for bounded function. So function defined on closed interval a comma b. So let f be the function. This f be a bounded function. Let f be a bounded function on the closed interval a comma b. Suppose we have a two partition. So let capital P1, P2 be two partition. Two partitions of the interval a comma b. Suppose P1 is the refinement of P2. That is, if P1 contains more points than P2. Okay, suppose P2 contains 10 points, then P1 contains at least 11 points, maybe 12 points or anything. Suppose P1 is contains P1 contained in P2 contains P2, then what is the relation between this lower sum with respect to this partition? What is the lower sum with respect to this partition? Then the first point. As I already said that, so therefore we can talk about the lower sum of the function with respect to P1, and then lower sum of this partition P2. So what is the relation? And similarly, what is the relation between upper sum of this partition P1 and then upper sum of the partition P2? So I already said that if the number of points is increases, the lower sum is increases. Now P1 contains more points. Therefore, the lower sum of P1 is bigger than that, the lower sum of P2, because P2 contains less number of points. But here we get less than or equal to. Okay. Now the lower sum are always less than or equal to upper sum. Even if you take P1 or P2, the lowest sum of any partition P1 comma F is always less than or equal to upper sum of any partition P2 or P1 or anything. Okay, but this is less than or equal to, we know that by 2, this is u of P2 comma F. Anyway, we know this one. Okay. Now, one more sum is there, that is oscillatory sum. So oscillatory sum is nothing but subtraction of upper sum and lower sum. We define oscillatory sum. Oscillatory sum. The oscillatory sum is denoted by W of P comma F with respect to the partition P is nothing but upper sum minus lower sum. The upper sum minus lower sum is defined to be oscillatory sum. Okay. Now, what is the relation between this W of P1F, W of P2F? So, what is the guess? Anyone? What is W of P1 comma F and then W of P2 comma F? Because P1 contains more points, P2 contains less number of points. Therefore, what is that? Is less than or equal. Because sum also, the subtraction also reduce, right? Therefore, we get this one. Okay, so okay, which one contains P1 contains more points. Therefore, P1 is to be less than this one. Now, what about okay? Any doubt so far? And then what about sum?
No, sir.
Yeah. Okay. Suppose we have sum of two function. What is the lowest sum of the partition of your sum of two function? All the things I can write as a statement, and then we will solve some problems. Okay. Theorem. Suppose we have two function f and g. So let f and g be two bounded function. So let f comma g be bounded function. Defined on closed interval a comma b. Okay, and we have a partition P, and let capital P be any partition. Any partition of closed interval a comma b. Then the sum, lower sum of the sum of two functions. Then lower sum of the function f plus g with respect to the partition P is always greater than or equal to lower sum of the function f with respect to P plus lower sum of g with respect to g. Okay. And for upper sum is smaller. So the second one is the upper sum of f plus g with respect to the partition P is less than or equal to upper sum of f with respect to f with respect to P upper sum of g. So this is always true. Okay. Okay, now maybe some more theorem is there. Now we discuss some examples. Example, compute the lowest sum of a function with respect to P and upper sum. So the first problem is the function f of x equal to x square. F of x equal to x square on the interval close to number 0, 1 with the partition P is 0, 1 by 4, 2 by 4, 3 by 4, 1. So this is a partition of closed interval 0, 1. Now the second problem is f of x equal to x. If we take the function f of x equal to x on the same interval close to 0, 1, the partition P is 0, 1 by 3, 2 by 3, 1. Okay. Now what is the first you have to find the lower sum, upper sum of the first function. Okay, solution. Now, what is the subintervals? So, for the first problem, the subinterval maybe I call I1. I1 is a subinterval 0, 1 by 4. Subinterval. Another subinterval is 1 by 4, 2 by 4. The I3, another subinterval is 2 by 4, 3 by 4. And then I4 is 3 by 4, 1. Now, what is the lower sum? So, I already said that the minimum value of, so if you look at this interval, if substitute the points 0 to 1 by 4 and the, because what is the graph of f of x equal to x square is nothing but parabola, right? Is increasing. So, in the 0 to 1, if you split the points, so it's always increasing. Therefore, in the first interval, the minimum value is 0. That is m1 is 0. What is m2? In the second interval, you will get a minimum value at the point 1 by 4. Therefore, 1 by 4 square is nothing but 1 by 16. What is m3? Small m3. This is 2 by 4 whole square. 2 by 4 is nothing but 1 by 2. 1 by 2 square is nothing but 1 by 4. Right? Now, m4 is nothing but the minimum value of the function at the last interval 3 by 4 square. So, 3 by 4 square is nothing but 9 by 60. Now, what is the lower sum? L of p, f. m1 into length of the first interval is 1 by 4. m2 into length of the second interval, everything is 1 by 4 because all the length are 1 by 4. m4 into 1 by 4. Now, substitute the values m1, m2 value here. So, 0 into 1 by 4 is 0 plus m2 value is 1 by 16 into 1 by 4 plus 1 by 4 into 1 by 4 plus 9 by 16 into 1 by 4. You can take 1 by 4 outside. You will get 1 by 16 plus 1 by 4 plus 1, 9 by 16. Okay, so if you want, you can take 16 also outside. Therefore, 1 by 4 into 16. Therefore, we'll get 1 plus, and here 16 is there, therefore 4 plus 9. So, 14. 14 by 9 into 16. Correct? Or I did any mistake? Oh, sorry. Correct, 1 by 4, right? What is M2? Okay, I have to take, okay. This is 1 by 16, right? Because 1 by 4 square.
So 2 by 4 is 1 by 2 only, sir.
Sorry? Where?
In M3, how
Okay,
1 by
M3.
4 comes?
What is, we will get a minimum value at the point 2 by 4. So 2 by 4 is nothing but 1 by 2. 1 by 2 square is nothing but 1 by 4, right? Therefore, this is correct. And here 3 by 4 is correct. Now, finally you have to simplify. So this we can cancel by 2. Therefore, 7 by 32. Right? So this is the lower sum of this one. Now, what is the upper sum? So therefore, what is capital M1, capital M2? So again, you will get a maximum value at this endpoint. 1 by 4, 2 by 4, 3 by 4, and then 1. So therefore, capital M1 is nothing but 1 by 4 square is nothing but 1 by 16. M2, capital M2 is 2 by 4 is nothing but 1 by 2. 1 by 2 square is nothing but 1 by 4. M3 is nothing but 3 by 4 square is nothing but 9 by 16. M4 is nothing but 1 square is nothing but 1. So length is always 1 by 4. Therefore, 1 by 16 times 1 by 4. You can take 1 by 4 outside because all the subinterval length is 1 by 4. Therefore 1 by 16 plus 1 by 4, m2 plus m3 is 9 by 16 plus 1. Now you have to simplify. So you can take 16 outside. Therefore 1 by 4 into 16 times 1 plus 4 plus 9 plus 16. So this is actually 20, 30. 30 by 4 into 16. You can cancel 2, therefore 15 by 32. So this is the upper sum. For the first function f of x equal to x square, with respect to this partition 0, 1 by 4, 2 by 4, 3 by 4, 1. So similarly, you can find the lower sum, upper sum for this function with respect to this particular partition. Okay. Now, there are some important things. If you take any constant function, is always integrable. So integrable means what? The lower integral value, the upper integral value, both are equal. Then we say such a function is integrable. So there are some theorems. Any continuous function is integrable. Before that, state one more exercise. Show that any constant function is integrable. Show that any constant function is integrable. Integrable means what? Riemann integrable. So how to prove this one? Constant function means what? Everything maps to some fixed number. So solution, suppose f is defined on some, if you take any interval close interval a comma b. So f of x equal to some k for all x in the interval close interval a comma b, because it's given that constant function. Therefore everything maps to some constant. We call that constant is k. So we got to prove that this is an integrable function. Therefore if we take any partition, so we start with the arbitrary partition, let p equal to the first point is x0 is a, and then some x1, x2, etc. xn minus 1, comma, the xn should be b. Be any partition. Be any partition of the interval close interval a comma b. Now first we have to find the lower sum, upper sum, and then you have to take the infimum and the supremum. Now, anyway, the function, the minimum value, maximum value, everything is k because it's constant function. If you look at the graph of the function, suppose this is k, the graph should be this our f of x. So just like. So if you take any a, b here, you will get this our region. You will get actually a full rectangle, exact rectangle. So the maximum value, minimum value of if we take any subinterval is always k. Okay. So what is the lower thing? Lower sum of this. That is all small mi's are. So by the definition, this is nothing but summation mi into or mr into delta r, where r equal to 1 to n. So each mr's are k, you can take k outside, therefore summation delta r. So summation delta r is nothing but length of this interval, that is k into b minus a is the sum of all the subintervals. Therefore the lower sum is this one. So what is the upper sum of these? By the formula capital mr into the length of the subinterval, where r equal to 1 to n. So since each mr is k, you can take k outside, therefore summation delta r is nothing but b minus a. Now this is for single partition this. If you take the supremum of all lower sum of f, this one. But here should always constant, is not depending upon the partition p. Therefore supremum also k into b minus a. Again, if you take an infimum of all the upper sum for any partition p, you'll get the same thing because everything is constant. So both are exist and both is equal. Therefore integral a to b f of x dx equal to the common value, that is k into b minus a. So this is nothing but actually integral a to b, what is f of x? K into dx. If we take k outside and then integral dx, we get x. Upper sum lower, upper limit, lower limit is k into b minus a. So therefore, if we take any constant function, is Riemann integrable. Okay, this is very important. Now, maybe we can there are some more examples are there. Okay, that is better thing is. So now show not every bounded function is Riemann integrable. Okay, so the minimum condition is required is bounded function, but not all the bounded functions are Riemann integrable. So what is the example for that? So that is a bounded function need not be Riemann integrable. So every bounded function need not be every bounded function need not be Riemann integrable. Riemann integrable. So this is given example of a bounded function which is not Riemann integrable. That is very important example. So maybe we can define that. So the f of x function is defined to be, if you take any interval, okay, defined on closed interval a comma b, is defined to be 1 if x is rational in the interval. So otherwise I can write, okay, for 0 if x is rational. X is rational in the interval close to a comma b, because we defined on close to a comma b. For rational points, it maps to 0. For irrational maps, it's to 1. So if x is irrational points in the interval close to a comma b. So clearly the function is bounded because it's bounded by 1. Now we are going to show that this function is not a Riemann interval. Now if you take any partition, the lower sum, upper sum need not be equal. So suppose if we take the partition P, so I take A is the first point, that is x0, x1, x2, etc. Xn is B. Now, what is lower sum of the partition with respect to the function? That is small m1 into delta 1, m2 into delta 2. Delta 1, delta 2 is nothing but length of the subintervals. So mn into delta n. Now, what is m1? So if you take any interval, the interval is always contained in rational numbers as well as, suppose A is here, B is here, suppose this is x1 and this is x0. So the function is like this. But this is not a function actually, because the function take only 0 and 1. Okay, it's not possible to write the function exactly. Now anyway, if we consider this first interval, this interval contains rational points as well as irrational points. What is the maximum value? And what is the minimum value? Minimum value is always 0, maximum value is always 1. Therefore, all the mi's are 0. Therefore, 0. Because all the subinterval contains rational points as well as irrational points. The corresponding f is 0 and 1. Therefore, the lower sum is always 0. Now, what is the upper sum? So, upper sum is nothing but capital M1, the maximum value of the function into delta 1 with respect to the first interval. M2 into delta 2, etc. M into delta n. Now, what is this? All the mi's are 1. Therefore, delta 1 plus delta 2 x plus delta n, this is nothing but b minus a. So now, so since here we get the, for any partition P, we get the L of the lower sum is 0. If you take the infimum, if you take the supremum of all the things, you'll get 0. So therefore, supremum of all the lower sum, you'll get 0 again. So because it's constant. Now similarly, for infimum of all the upper sum of any partition P, again you'll get b minus a. Because b minus a is constant. For single partition, you'll get constant. Therefore, if you take vary all the partitions, still you are getting b minus a. So therefore, the upper integral is b minus a, but the lower integral is 0. But here upper integral not equal to lower integral, because b minus a not equal to 0. So it's happen only when a equal to b. But we are taking the interval a b, therefore a not equal to b. So therefore the function is not integrable, because the lower integral not equal to upper integral. Therefore this function is not Riemann integrable. But the function is bounded function, but not Riemann integrable. So this is very, very important example. So first you got to find the lower sum, upper sum of a function. If you take arbitrary arbitrary partition. Anyway, we have some more theorems there we will discuss in the next class. Okay, thank you.